Hi students, welcome back to geology. We are now going to move on, now that we know something about crustal deformation, we're going to move on to folds, and this is when rocks bend. So rocks are bending to accommodate that stress. We're looking at ductile deformation here for reference. So as you listen to this video, I want you to ponder, how do you think thick, solid rock layers could end up curved or wavy instead of flat? So I've already kind of given you some of that background today, but you are going to learn more about it in the next couple of slides. All right, let's start with folds. So let's look at the definition and how they form. So folds are bends or ripples that develop in rock layers due to compressional forces. So you are only going to see folds if the rocks experience compressional stress. If the rocks experience shear stress, so sliding past, or tensional stress, pulling apart, you are not going to see folds. Okay, so this is compressional stress driven accommodating only. Okay, they can be classified by their shape, size, and orientation. And we describe their orientation by understanding where the axis is, or the axial plane, and the limbs. Okay, so the axial plane is the plane that splits it into. So if you imagine a piece of paper, we have a piece of paper here, and we bend it, that center point that would split the paper in two right here. Whoop, there we go. Right here is the axial plane. And then either side of that axial plane is the limbs. Okay, there's also a diagram right there for you to reference that shows you the axial plane, the plunge line, which is going to be the direct going, and then the limbs on either side. Okay, we also have the fold axis, which is the line along which the bending occurs. That's very similar to the axial plane. And then the hinge line, which follows the line of greatest bend in the folds, wherever the greatest bend is, and then the limbs are the two sides. Okay. Now, sometimes these folds are oriented different, in which we might use the term plunge, and we'll talk about what that looks like in a second. So the different types of folds. Folds are bends or waves in the rocks that we can see. So these rocks are no longer horizontal, which we talked about undeformed strata versus deformed strata. Undeformed strata are going to be horizontal. Deformed strata are going to have some sort of fold or wave in them. And then we can start identifying what they are. Are they anticlines, synclines, monoclines, domes, or basins? Okay, so we'll look at each of those individually in the next couple slides. But these folds can either be symmetrical, which means that the limbs are equal on either side of the axial plane. They could be asymmetrical, which means that the limbs are at different angles, or there's not a vertical axial plane, or they might be dipping. They can be overturned, which means that the axial plane is steeply dipping in one direction, and the limbs dip in the same direction, but usually on different dip angles. Or they can be recumbent, which means they're almost horizontal again, or nearly horizontal axial planes. Or they can be plunging, which I used that word already. The axis of the fold would plunge into the ground. Okay, so let's start with the types of folds, and then we'll look at some of the special cases. All right, so anticlines. Anticlines are concave down, so they convex down. So it would be like if my paper went like this. And the reason, or the best way to remember these versus some of the others, is that they look like they kind of form an A for anticline. Okay, so the anticlines form an A shape or concave, convex down shape. And an example of this would be in California anyway. We have a couple of examples. The Anticline Ridge that's east of Coalinga, and then we have the Ventura Avenue Anticline, which runs through Ventura, which is in Southern California. And so anticlines are very special in that they can also create something that is a very hot commodity, and that is oil. Anticlines can form what we call an anticline trap, where natural gas and oil can get trapped. So a fold structure with an arch like this can form non-porous rock overlaying porous strata, which is the reservoir rock that holds the actual oil. and then it can trap that oil, gas, or water until we drill a well and pull it out of the ground. And so when geologists are looking for areas to mine for oil and gas, they are looking for anticlines in the subsurface. Opposite an anticline is what we call a syncline. So if I took that same piece of paper and I folded it the other direction like this would be your syncline. And they make a U shape, or maybe it looks like you can fit a big S in it, is a good way to remember it for synclines. So they are concave up shape. And a really good example of this, wow, there's a lot of misspellings in here, is Rainbow Basin in Barstow, California. That's what this picture is from. It shows the beautiful colored sedimentary layers folded in a concave up fashion. Okay, next we're moving on to monoclines. Monoclines are similar to synclines, or sorry, anticlines in the way that they are shaped, but they are more like steps. They're not a full, big, exaggerated fold. They are step-like folds, and most of the time these are created from what we call thrust faults. And these faults are oftentimes not propagating to the surface, and we'll get to them again when we get to faults. But for now, know that they create this little step. So they move things up and creates this little folded step at the top. An example of this in California would be the Chico monocline fault. It's very subtle. You can see it a little bit in this cross section. Over here on the left, you can kind of see the step up there. And then there's a little bit more on the right. And again, these faults don't propagate all the way to the surface, so they end up folding the layers that overlie the fault. When we get into domes, domes are a usually symmetrical to semi-symmetrical upward bend of rock beds. So we have a bunch of rock beds bending up and kind of forming this dome-like shape. And when it erodes, you can see kind of circles, concentric, that's the word I was looking for, circles of the different rock layers as it's eroded away. So there's a diagram there for you to see. It's basically like it looks like a bowl overturned. And then on the right-hand side there, that's what it would look like in map view. Basins are just the opposite of that. They are the bowl face up. So they are an inverse of a dome, and they are a depression in the rock strata. And again, as things start to weather, you can start to see concentric circles of different rock formations. All right, so a little activity for you to write down in your notes. Looking at these 4 diagrams, which folds do you see? How many of these folds do you see? I'm not going to give you the answers in the video because I want you to work on that. So in figure A, how many folds do you see? What types of folds do you see? And do that for each one. And then our final thoughts for this video. Folds are caused from ductile deformation. We can get anticlines, synclines, monoclines. We can see them plunging. We have domes and we have basins as well. And for your final thought, I want you to write down in your notes, what does the presence of folded rocks tell us about the type of stress that acted on them? So what kind of stress were these rocks experiencing in order to accommodate that stress as folding? All right, I'll see you guys in the next video. Bye.